Okay, we're going to begin this review of one-dimensional conduction with the expression for Fourier's law. Fourier's law is an empirical expression, and it's also a vector equation because the heat flux or the rate of heat flow is going to be a specified direction. And the magnitude of this heat flux is going to be proportional to the gradient of the temperature. And the temperature field is going to be written in terms of the coordinate system that we're working with. For instance, if we're working in Cartesian and we'd be in 3 dimensions, we'd be writing the temperature field as a function of the x, y, and z coordinates. Now, the direction of the temperature of the heat flow is going to be downhill from hot temperature to cold temperature. In evaluating a gradient, that direction is typically given to be a negative, so we multiply through by that negative sign, and that would give us a positive. So what we're essentially saying is that the heat flow is from hot to cold. Now, if we rewrite Fourier's law in 1D Cartesian form, and we multiply through by A, so converting the heat flux to a heat rate, this ends up being the expression that we come up with. And notice we have a dt dx, so where t will be a function of x, as of yet unspecified. Now our units, sticking to the SI system, area is of course meters squared. The gradient, even though it's an unspecified function right now, is still going to have the units of Kelvin per meter. Our heat rate is going to be the rate at which energy moves. So energy, thermal energy, is given in joules, and joules per second gives us watts. As we said, the heat flux is just the heat rate divided by the area. In this case, it would be watts per meter squared. And K, our thermal conductivity, gets the units of watts per meter per Kelvin. Now, it's very important to point out that in the 1D Cartesian form, the area that the energy will be passing through is going to be independent of the independent variable x. Now we can also write Fourier's law in 1D cylindrical form, and in this case, however, the area that we're going to be looking at, the area of a cylinder, is going to be dependent upon the one-dimensional coordinate in this system, which in this case is r. So we're going to be able to write area is 2 pi r, and in this case times L. L is going to be the length of the cylinder, so there's going to be no variation of temperature in that direction, and sometimes we will report the heat rate as per unit length. Now, again, I'm just writing out specifically that area is a function of r, so that we can write the 1D cylindrical form of Fourier's law and substituting in 2 pi RL for the area. And we see that our temperature coordinate, or the temperature function, is going to be T as a function of R. So our temperature field will only vary in the radial direction. Now, in order to utilize Fourier's law, or calculate the heat flux or the heat rate, we're going to need to develop expressions for the temperature gradients. Or to get the temperature gradients, we're going to need the temperature fields. And in this case, for the Cartesian form, one-dimensional, we need the temperature field T as a function of x. And for the 1D cylindrical form, we're going to need the temperature field as temperature as a function of r. And of course, we're going to utilize the heat equation to come to these, and we'll do this in the next review slide.